Welcome to another episode of Unposed British Science Week podcasts, and we're very excited about this one where we get to see some very cool experiments. If you're able to, we really recommend that you watch this episode on our YouTube channel, UOM Phys Outreach, where you can see it for yourself.
Hi, my name is Annabella. I am a third year undergraduate physics student at the University of Manchester. And I'm also the Events Manager for IMPO. And today I'm here with...
My name is Draga Pihler-Puzović. I'm a senior lecturer at the University of Manchester. I'm also a researcher there. So really nice to meet you all.
Great, amazing. Right, so do you think you could give us a short introduction to the topic we're going to talk about today, which is, in general, nonlinear physics?
Cool. So that's a framework, nonlinear physics, and I guess the main thing to think about in that phrase is the word nonlinear. So what do you think about when you think nonlinear? Well, let's start with linear first. And when you think linear, the first thing that comes to my mind is, relationship y equals ax, right? That's something that we've learned back in school. And so that's a linear relationship. That's some sort of proportionality between the variable x and y, right? And what's nice about this relationship is for any pair x1 and y1 and x2 and y2, if you consider any composition or sum of these two, you still get the same relationship. So, for example, y1 equals ax1, y2 equals ax2. That also means that y1 plus y2 will be equal to a times x1 plus x2. So you can build any number of solutions to this relationship in that way, right? That's just this work because it's a linear relationship. Now, as long as you keep to that, it's all very simple. But as soon as you become even a little bit nonlinear, so add a sort of a non-one power to either side of this relationship, this no longer works. It's no longer as simple. You can't find new solutions by adding to previous solutions, right? That's kind of the nonlinearity in this relationship. So let me just sort of demonstrate that. So here I'm going to add a square to an x. We have y equals ax squared. And so now if we try and do that with solutions, x1 and x2, then we can no longer write this relationship, right? It no longer works. So y1 plus y2 is not going to be actually equal to a times x1 plus x2 squared, right? And that's a feature of nonlinearity, that you cannot add solutions. And that kind of idea translates into nonlinear physics as well. That just by knowing a certain number of solutions doesn't mean that you can predict what your system is going to do by adding up those solutions. That's kind of the essence of nonlinear physics. And as you can imagine, someone very wise on the internet once said, there are more non-bananas in the world than bananas. So there are more physical problems that are nonlinear than physical problems that are linear.
Cool.
So that's kind of a short explanation of nonlinearity.
Amazing. Right, what do you in particular do as a researcher in this field?
Right, so in our group, we apply the ideas of nonlinear physics to different physics phenomena that you can sort of observe around yourselves. And on this scale that is sort of tabletop type experiment, basically. So we're not dealing with particles, fundamental sort of physical particles. We're not dealing with stuff such as stars or, on that scale. So we're dealing on a sort of intermediate scale. So we're trying to apply the framework of nonlinear physics to these kind of phenomena on the intermediate scale of physics. And in particular, we're interested in physics of fluids and physics of somewhat different fluids like gases and liquids, physics of soft structures, so structures that sort of deform and either deform reversibly or sometimes we also look in irreversible deformations. So these are kind of general topics, and we apply ideas of nonlinear physics and framework of nonlinear physics to phenomena appearing in these sort of systems.
Okay, it sounds really, really interesting. Could you show us some of the examples of?
Yeah, so let me start with very simple ones. So here is kind of this was a toy when I was a kid. This is a toy we could pick up on markets and stuff. So here it's just a metal loop with a bit of a sort of bowl at the end, and I'm just going to rotate it basically, okay? And that ball happily sits at the bottom of this loop because that's a sort of equilibrium for that ball. So what does that mean? It means that all the forces balance, and as we know from Newton's law, this ball doesn't want to go anywhere. It's happy sitting there. Now the only thing I'm going to change now is I'm going to start rotating this loop a bit more quickly, and let's observe what's happening to the ball. Okay, so that's the only thing that I'm doing. And you can see that magically ball kind of no longer sits at the bottom, but it's actually moved upwards and found a new equilibrium position, so a new position where it's happily sitting. And again, at that point, all of the forces again balance, right? So that's because this problem is nonlinear, and you're going from one equilibrium position to another. So that's the type of a question that you can ask yourself. How many equilibrium positions are there in the system? And how you can go from one point to another, for example. There are lots of exciting sort of consequences of this. So one that's probably the most in popular sort of science, and the one you might have heard of as a sort of non-physicist, is question of chaos, right? Chaos, question of chaos, and the so-called butterfly effect. So what happens if, for example, in this popular culture, Back to the Future films and stuff like that, if you go backwards in time and change some event by a little bit, and then you get a completely different outcome down the line. So this idea that you get different outcome is a consequence of chaotic behavior of the system. And let me demonstrate that using another example. So here's a double pendulum, okay? Yep. And that double pendulum basically is now in equilibrium position. Is that this whole thing is, I'm not touching it basically, but I'm going to just start sort of playing with it a little bit. So I'm going to let it go by sort of putting it upwards. So I'm just going to demonstrate what happens to this pendulum as I let it go. So I'm kind of putting it in upright position, and I'm just releasing it without applying any additional sort of velocity to it. So I'm not pushing it very hard. I'm just letting it go basically. Let's see what this pendulum does. So it does something funky, right? It's moving about. Is behaving very unpredictably. It's doing some sort of God knows what, some dance basically. All right, and then eventually, because we have frictional forces here, so there is friction, because there are parts that connect different bits of the pendulum, everything is going to sort of calm down, and it's going to stop oscillating and basically return back to the equilibrium where it was. But you can imagine that in some sort of different reality where there is no friction, we can keep this thing going forever, and forever it's going to do these funky kind of movements of taking different positions and doing all sorts of things. So now I'm going to sort of repeat this again, doing exactly the same thing. So I'm going to sort of stop it all together and start from this initial position. And this is a bit like our heroes from popular movies going back in time and sort of starting from the same position. But of course, not starting at exactly the same position, because I'm not doing this experiment very precisely. I'm sort of attempting to do it precisely, but of course there are slight changes compared to the previous time. And so if I now let it go, this pendulum is going to do something completely different, actually. As you can see, it's like we've decided not to do much of the funky behavior, but instead it's kind of nearly almost immediately sort of doing these kind of quite boring oscillations and all sorts of other stuff, right? So this is a consequence actually of chaotic behavior. Eventually it's going to stop, of course, because there is friction. And I'm going to just speed it up and stop it here. So this is the consequence of this chaotic behavior. So there is nothing, because we didn't know precisely the initial conditions we started from, the system ended up kind of going through this sort of trajectory, following this behavior in space and time, which was completely different the first time around, the second time around, right? And that's because even though we've tried to start with exactly the same initial conditions, we haven't actually. And we started slightly off, with slightly different initial conditions. And because of the chaotic behavior, the outcome of these slightly different initial conditions ended up being completely different. So that's kind of another consequence of nonlinearity in the system. And one might also ask, when you have these multiple equilibria potentially in the system, do we necessarily go from one to another, or maybe like in the chaotic systems, we just explore endlessly different kinds of equilibria and move between those, and so on. So there are all these kind of interesting questions you can ask. And of course, if you go back to movies that we know from popular culture, then there any sort of small perturbations or many small changes to initial conditions end up with massive changes down the line. That's exactly what's kind of same in nonlinear systems.
Amazing. Really cool. Right. Coming back to you specifically.
Sure, of course.
What is your particular area of research?
Okay, so what I do in particular is I'm studying instabilities in these fluid systems, so systems that include liquids, and in soft structures as well. So what are instabilities? Again, it's a question of sort of stable versus unstable. You can think of instabilities as kind of a way from nonlinear system to get from one equilibrium position to another, and sort of how it gets there, or to kind of leave one equilibrium system and forever do something funky afterwards. And there are all sorts of different scenarios in which that can happen. So that's what I'm interested in generally. More specifically, I can show you a few examples actually. So I have some examples. I'm going to use, so all of these examples include sort of different soft matter problems. So these are different sort of soft materials. So the first one is with liquid, the second one is with the elastic structure, and the third one is actually with grains and some muesli that I have back on that shelf in my kitchen. So let me start by showing you an example with the liquid. So here, what we're having here is, this is called a halogen cell, but these are just two plates very close to each other. So a very small gap in between. And what I'm going to do now is I'm going to inject some very viscous liquid in between those two plates. What I'm doing basically, I'm taking a little bit of golden syrup. So here I have my golden syrup. And the only thing I did to it for it to look so dark is I've added a bit of food color to it. So you can really do this experiment at home if you want to do this demo. Okay, and then otherwise it's just two plates, very small gap in between, and I'm injecting some of this fluid in between. So if I do that, so let's see, a bit of air to begin with, but otherwise you can see that there is a bit of basically circle. Nearly, it's not a very good circle because there is a bit of air to begin with there, but it's a pretty good circle to, it's a circular blob that's expanding basically. Nothing much going on, right? Not particularly interesting. Just a bit of liquid penetrating a small gap in between two plates. Now I'm gonna just get rid of this bit. I've made another cell on the side, another cell, just to demonstrate what I'm after. So basically, it was just a little bit of gooey liquid. And now what I'm going to try and do is I'm going to try and displace this gooey liquid by injecting some air into it. So I have another syringe, which is basically just an empty syringe with air. And I'm going to try and push this gooey liquid out of this gap in between the two plates. The reason, this is a fascinating nonlinear physics actually experiment, and I'll explain why in a second. But it's also of lots of practical issues, lots of practical interest, because, people, try to display all sorts of things in between small gaps. For example, when they are, drilling for oil and trying to displace oil, that's what they do. They fill in, they basically fill in those pores or those rocks with water and trying to push out oil and collect it somewhere. So here I'm just injecting air. Let's look at what happens. Don't blink because it's a very quick experiment. Okay, so remember when there was no air, when we were starting with the liquid, it was all a bit circular and boring. So now there is air. So watch what happens. Okay, so now as you can see, it has nothing, it looks nothing like a circular boring interface. In fact, it has a very complicated sort of structure, this boundary between air and liquid. And it's a consequence of nonlinearity in the system, right? And what's fascinating about it, why we are so interested in the system, is that the whole nonlinearity is actually contained at the interface, at this boundary between the two fluids, between gas and liquid. And so you can kind of watch the development of this instability or transition from one state, which was circular and boring, into something more exciting and sort of growing, right? And then you can even ask questions such as, is this a disordered propagation? Is there an order to it? Or is it a little bit like those chaotic sort of things that we've seen before where there is something more interesting going on? Okay, so that's kind of the nonlinear take on it. But you can also ask a question as a physicist, what's the explanation for what we're observing? Why are we observing this phenomenon? Why is it fingering in the first place? And let me come back and tell you a little bit more about that. So here I am. So basically, there's a question of why do you in the first place? There's a perfectly nice solution in the system where everything is circular and boring. Why would you ever do something else? It turns out that physics is what's pushing you there to do these things. It turns out in this system, it's all relatively simple at the point where the instability starts developing. It's a competition between two forces in the system. So the first one is viscous force, where it's a measure of friction in your liquid. So here is an example of a liquid which is very viscous. In other words, has a very big internal sort of friction. That's the liquid I was displacing. The other force that's important in the system is surface tension. And the surface tension is the force that acts whenever you have a boundary between a liquid and some other fluid, for example, gas. And you think about it, ever since school, we know about menisci and the fact that at that surface of the water, you have the deformation of the surface is never perfectly flat. So the same force acts in the system as well. So the competition between internal frictional forces of the very viscous liquid and the forces at the interface is what eventually leads the system to leave the circular equilibrium, where it was relatively happy, and start propagating in a slightly different shape to before, basically, in developing these figures. So that's the first example I was going to show you. The second example I was going to show you, it has to do with elastic structures. So I'm here having one elastic structure. I'll have lots of bits of it. So let's see. Here we have, let's start with the ruler. Here's one elastic structure. So why am I saying it's elastic? If you take a ruler that you have at home and start deforming it, then start applying force, say pushing on it on either side, then it's eventually going to snap or buckle sideways, right? It's going to go to the side. And then if you remove that force, it's going to happily become a ruler again. Of course, you don't press too much because it will break it. But there is this part when the deformation that you apply to the ruler while you're pressing on it is elastic. It's reversible, right? So that's a ruler. Now I'm going to have something else which is similar like a ruler, basically. It's the same, it's a column, but instead of having sort of a solid structure like a ruler, it's going to have some holes in it, right? And it's made of a rubber, but that's not the principle here. I mean, that's not the principal feature of it. It can be made of all sorts of other materials, and will even sort of hard materials like metal, it will still do similar things. So basically, the question is, if when I compress this structure, which is just like a ruler but has some holes, is it going to do the same thing as a ruler? Is it going to just go sideways, right? So let me try and do that, so you can see that as I'm compressing it, hopefully, I'm not holding it very well, but you can see that actually it doesn't really go sideways, but instead it stays upright, and it kind of deforms in a very different manner compared to the ruler. It assumes this kind of very interesting shape. We call that an alternating pattern shape. And the reason why it doesn't go sideways like a ruler is that because it's basically accommodating the same type of deformation, so only on a different length scale. So if you look very carefully at my sample, you can think of it as being made of lots of little rulers that connect different holes, right? So some of them are horizontal, some are vertical. So what happens as I deform the structure is that on the length scale, on the level of those individual bits that make up the whole bit, that's where it goes sideways, right? And there's some sort of sideways deformation there. So this system, we've changed it just a little bit compared to ruler. We put some holes into it, and yet it started doing something very different, right? And so That's because of, again, non-linearity in the system. And you can imagine that there are, if you think of these bits as lots of little rulers, then you can imagine there are lots of different directions in which each of the bits can deform, right? So this one can go sideways that side, that one can do something else, and so on. So there are lots of possible solutions here, and yet it chooses one. So one question you can ask as a physicist, why does it choose to do what it does, basically, right? And so that's another sort of example. You can then play with that example, play with it with different materials, make it much bigger. So here's a whole sheet of these. If you deform that sheet, interestingly, it still does the same thing. So it still does the same pattern, only on a different sort of scale yet again, right? It's on the scale of the whole sheet. So it's a very robust sort of phenomenon, very robust thing. And yeah, that's another example for nonlinearity. The reason why you're seeing this is because the system is nonlinear, and again, because it does this instability of buckling on the small length scale that connects different holes. So it does this sideways movement, left or right on that scale. Okay, so that was my second example. My final example is to do with dry particles and dry grains. So here's one. It's a question, philosophical question. Have you ever tried mixing muesli so that you get the best muesli at the top? One thing we would naturally want to do is say shape it. Right? That's one way of kind of trying to mix things. When you steer, you also mix things. So that's kind of something that naturally occurs. So like as an idea. So let's try and shake this. So if you shake this to mix this, actually what you end up doing is completely demixing it. So all of the big bits or big particles here are at the top. You can see them as sort of metal balls, and all of the red particles, which are much smaller, are at the bottom, right? So instead of mixing the system, you completely separated it. This is what happens with your muesli. So I'm going to bring my muesli over. These are not quite muesli, but still work. These are flakes. So if you look at my bag, what you can notice is that all the small bits that no one wants are at the bottom, right? And all of the good bits, big bits, are at the top. And that's because as we're carrying our food from supermarkets and stuff, we're naturally also kind of shaking it, right? So that's the separation happening in the system that's very much nonlinear. The reason why it's happening is it's very simple actually. It's because as you're shaking stuff, the main force that acts in this physical system is actually gravity, right? It's plus your sort of force of shaking, right? So what gravity does to little bits, and as well as big ones, as they fall down, the little bits find space and they percolate through like bigger bits, getting slightly apart as you shake up and down, up and down. And so all of the little bits that go through the sort of in between the large bits end up being at the bottom, where they eventually happily sit. So that's kind of the mechanism for why these particles are separated. It's all to do with spacing between different sort of big particles versus sort of small particles being small enough to kind of go through. So that's another example of non-linearity, but this time it's sort of with dry particles, I guess, and with another example of a soft system that we are interested in, so tabletop size.
Amazing, really, really cool.
There's lots. I don't know. You probably want to stick to one or the other. It's probably lots of examples.
It's great though to have like physical representations of things. It's really
okay.
Two hopefully smaller questions left.
Okay, yeah, sure.
And more about you.
Okay.
Right. So, how did you get into this career as being a physicist, a researcher? And did you always think that this was the job you'd be doing?
I think it's by accident, but I think I'm not the only person like that. When I was in school, I was always thrilled by, I would get adrenaline rush every time I would understand something or I would solve a problem and it was the correct answer. I like that. And so I kind of knew I was going to do maths and physics, which is what I ended up doing at the university. And then gradually, as I was doing more and more experiments as a part of my degree, getting exposed to more and more ideas, I just started enjoying these kind of research projects, to just working on an idea. So first making an observation and then sort of developing it into a problem, and then eventually getting the answer to that problem. And so it was the same adrenaline rush I would get as when I was in sort of undergrad, when I was in school, and then later on. And so that's how I ended up doing a PhD. And then when I started doing my PhD, and then afterwards as well, I was just excited every time. So it wasn't always, everything wasn't always perfect, but I would still get lots of these moments where I would get really, really excited about stuff that I was seeing and observing and solving at the end of the day. So that's how I ended up being a researcher, I guess. So it was very gradual process. It was growing on me. It wasn't something I decided to do when I was bored. it was definitely growing on me. I just liked doing it. Yeah, that's why.
That's great. And finally, what is your favorite part of physics? And also slightly a second question hidden in there, what is your favorite part of being a researcher?
So I guess what's my favorite part? I like the physics that you can observe around you, which is why I kind of got into nonlinear physics. I got into physics of fluids and and soft matter. I really like that physics around you. I like that stuff, experiments. I like kitchen experiments. I'm in my kitchen at the moment. I enjoy that part of physics, and I think it has lots of puzzling questions. There are lots of things you can, as a physicist, constantly ask about that. I like the combination of observation and doing explanations through theory and modeling. So that's what I do in my research. I combine the two. I think so. I like the luxury of being able to do that basically in my research field. Not everyone is as lucky. Some people are focused on, I think, in my opinion, some people focus on just theories and stuff that take decades to confirm, and then other people are more into sort of observational stuff, and I'm sort of in between, and I like that. I guess the second question was about what do I like about my job, or is that, sorry, I'm not sure what the difference is between the first question and the second question.
Sort of favorite part of being a researcher, and then also your just unrelated to that, your favorite little bit of physics that you really enjoy.
Okay, so I think I understood that. Okay, so I think I answered both. So my favorite little bit part of physics is definitely it's this framework of nonlinear physics and doing these instabilities, right? Trying to understand how the systems behave and go from different states, or what's their long-term behavior, that kind of thing. This is why I'm doing it. The favorite part of being a researcher is this formulating the problem, doing the problem, and getting the answer. I guess the whole thing. I really like researching. There are lots of other things that also happen with it that you kind of are less glamorous, and I guess as other people I don't like that as much. But the actual process of researching is really nice, and I think just kind of getting to the bottom of problems that ultimately I formulated, right? But I still think they're interesting problems in a context of everyone else's work as well. That's what I like the most.
Amazing. Great. Thank you.
Thank you for interviewing, by the way.
No, thank you to you.
Okay, do we have to say some byes to everyone?
I know, we could. Bye.
Bye. Thanks for watching.
Thank you for joining us for today's interview. We really hope you enjoyed it and that you will join us tomorrow when we meet Paul Connolly, an atmospheric physicist. Don't forget to like and subscribe and spread the word to your friends. The hashtag is BSW21 and our social media accounts are @UOM Phys Outreach.